Alright, looks like we skipped a couple of slides when we went from part 2 to part 3, so let's go back to this slide right here. Okay, so consider an ideal gas undergoing a reversible isobaric process. So it goes from P, V1, T1 to P2, V2, T2, but P1 and P2 are the same, so we're just going to call that P. And let's derive an expression for Q and W for that. And then we're going to consider an alternative path where we take a reversible isothermal process instead, followed by a reversible isochoric process, and derive the expression for delta U for that one. And then from that, we're going to verify that, in fact, for an ideal gas, Cp minus Cv is equal to Nr. Okay? So here's how we do it. Let's make a PV diagram here to visualize what's going on. So let's say this is P1, V1, T1. Okay, so here's our isotherm. So this is P1, and that's V1. So we're going to do an isobaric change. So we're going to go from V1 to V2. So we're going to call this V2 right here. Okay. So this is volume. And so V2 is going to be on a different isotherm, P2, V2. Okay. So P1 is equal to P2. So that's your reversible isobaric process. So what's Q for that one, and what is W? That's fairly simple. Q is equal to integral of Cp dt from T1 to T2. So that's just going to be equal to Cp, okay, times T2 minus T1. So it's going to be Cp delta T. Right? And our W is my negative integral of P external dV from V1 to V2, and our external pressure is the same as our pressure, it's constant. So it's minus P, which I can pull out of my integral, and then integral of dV is V, evaluated from V1 to V2, so minus P delta V. So that's your Q plus W. So delta U in this case is Q plus W. You say it's Cp delta T minus P delta V. Right? Now, let's take the alternative path this time. This time we're going to go isothermal. So we're going to take isothermal path there, number 1. And then once we reach the final volume, we're going to go isochoric. We're going to bring it up to the final temperature T2. This is T2. So let's calculate delta U for that process. Delta U for step 1 is just integral of partial of U with respect to V dt at constant temperature. dV from V1 to V2, and we already know that that is 0 because this derivative right here we've already shown to be 0. So isothermal expansion of an ideal gas, delta U is 0. For the isochoric heating, delta U for step 2, we're going to have integral of partial of U with respect to T at constant V dt from T1 to T2, and that's just integral of Cv dt from T1 to T2. So that's just going to be Cv times delta T. Cv is a constant. So we can then say that delta U for both steps, for both paths, is going to be the same since U is a state function. So we say Cp delta T plus negative P delta V, this is for the isobaric path, is equal to delta delta U1 plus delta U2, so 0 plus CV delta T. Okay. Or this is your isothermal path plus an isochoric path to get to the same final state. So let's rearrange this. You can see that Cp delta T minus, I'm going to move this one over to the left, so minus Cv delta T. So I'm going to move this one to the left, and I'm going to move this one over to the right. So that's equal to P delta V. I can factor out delta T here. I have delta T times Cp minus Cv is equal to P delta V. Right? But P delta V is just, since for an ideal gas, PV equals nRT, okay, at constant pressure, a change in volume for a fixed amount of gas would be equal to nR delta T. Okay, N is constant, R is constant, so a change in volume would be associated with a change in temperature. So this is P delta V is nR delta T. So Cp minus Cv times delta T is equal to nR delta T. And so canceling delta T, we can show that Cp minus Cv equals nR. Okay? All right. And that's what we verified. All right. So earlier this semester, we made the assumption that Cp minus Cv is equal to nR for an ideal gas. And from that, we show that for an isothermal process involving an ideal gas, delta U is equal to 0. This time around, what we did was we first showed from the fundamental equation, from the thermodynamic equation of state, okay, that delta U for an isothermal expansion of a gas, if you recall this from this previous slide, is equal to 0, okay, without making any assumptions about Cp and Cv. And this time we showed that Cp minus Cv is equal to nR. Okay, so in fact this is something you can derive as a consequence of the thermodynamic equation of state, which we won't be able to actually get to until we've done the first and second law, both first and second law of thermodynamics. All right. Going back to the Joule expansion, okay, we've shown that the Joule coefficient, partial of T with respect to V at constant U, is negative 1 over Cv times this expression right here, which we said is the partial derivative of U with respect to V at constant T. And we've shown that this is 0 for an ideal gas, but for a van der Waals gas, we've shown this also earlier to be equal to A n squared over V squared. So if that's the case, then you'll have negative 1 over Cv times A n squared over V squared. So that is the Joule coefficient for a van der Waals gas. So what's the significance of a negative value? You can see here that this value is going to be negative. Okay, all of the quantities here are positive, and you have a negative sign in front. What's the significance of a negative Joule coefficient? That means if you were to expand a gas, okay, and it obeys the van der Waals equation, expand it into a vacuum, your volume is going to increase, so delta V is going to be positive, your denominator here is positive, your temperature has to be negative. Expansion of the gas into a vacuum will lead to a drop in the temperature of your gas. Whereas we said earlier, for an ideal gas, that's going to be, there won't be any change in the temperature. What's the molecular significance of this? Well, if you're, again, you go back to your interaction potential, distance, potential energy versus distance between two molecules would look something like this, right? So if you're expanding, you're going from, let's say, an average distance here to here, you're increasing the average distance, you are in effect, okay? So if that's your total energy right there, expansion leads to a decrease in the kinetic energy. So this difference between the total energy and the potential energy is your kinetic energy. So expansion of your van der Waals gas would lead to a decrease in the kinetic energy, and so the temperature of your gas drops. Okay? Even though there is no heat flow and there is no work. Okay? So there's no work done, there's no heat flow, there's no energy change, but the temperature of your gas is going to drop.